Alright, so to round it off, this section on mathematical tools, I'm going to give you a few more examples on how spectra and autocorrelations look like compared to the original signal. And let's see first, so we're going to plot here the signal, the spectrum, and the autocorrelation of a signal. The first signal is white noise. So white noise is just static that you hear, for example, in the radio when there's no radio station on. That means that white noise has all frequencies in it, just completely random. The energy spectrum then looks like this. That means all of the frequencies are present in that signal, and they are all of the same amplitude. White noise is by definition uncorrelated. It's just completely random. That means it's only correlated to itself. So it's going to be 1 over here. But then the rest is going to be 0. I'll do that here and that. Okay. Alright, the next one is noise with the cutoff frequencies. That's sometimes used by electrical engineers if they want to test the system. They're sort of having a white noise where you have a lot of frequencies, but at a certain frequency you're filtering out all of the high frequencies. So you would not see much of a difference if you just look at the signal itself. But if you look at the energy spectrum, it's going to be 1 over here, but then there's a cutoff frequency, so somewhere over here it's cut off. The signal, because of, it's going to be a little bit more correlated because you're having taken out all of the high frequencies. So you're taking out some of the randomness, essentially, of the flow. So it still starts here at 1. It's just going to go down rather quickly over there to 0. So it's only correlated by itself. It's a little bit more correlated because you have not the very high frequencies that are disturbing. So next example is a sine or cosine function. So a signal you would get would be something like this. So you have only one single frequency with that in it. That means your energy spectrum is going to be 0 most of the time, except for this one frequency where you have a peak. So here you have this frequency of your signal. Of your sine function. Okay, so the correlation, how will that look like? So this one and this one are still correlated. But the further you go away, they're going to be anti-correlated at some point. So this, for example, if you're just taking this point, if S is very small, it's going to be starting at 1, of course. So it's going to be completely correlated. Over there, it's going to be uncorrelated. If you're comparing it over here, it's going to be anti-correlated. So every time you're choosing an S, that is exactly this distance here, then it's going to be anti-correlated. That means every time your signal is up here, it's going to be down there, and every time it's going to up, it's going to be over there. So you're choosing now here an S over here, so it's going to be completely anti-correlated. And this one, if you're choosing now an S that is exactly the frequency or the wavelength, it's 2, then you see this one's always going to be correlated. So you're moving down, they're always going to be correlated. So it's going to be going up here to N1. So the correlation is going to look like this. So this signal is always correlated with, or this peak is always correlated with this peak. It's always anti-correlated with this peak. So that's why you're getting this kind of signal. So remember, if you're calculating an integral length scale, if you're going back, we introduced the integral length scale tau. Usually it converges because you're integrating over this area. So for example, here you would get a length scale. If you're the integral goes to 0, but it would not go to 0 over here. So here does not converge. But luckily in fluid mechanics, you usually don't have a clear signal like that. So, but quite frequently you have signals that look like this, where you have a dominant frequency, like a sine function, but there's some overlay of some stochastic turbulence. And then the signal would maybe look like this. So you have a dominant frequency, but there's also some stochastic in it. So the frequency spectrum maybe looks like this. One dominant frequency. And again, dominant frequency. And the autocorrelation, so it's going to be somewhere in between this one and this one. So this one is just noise, or just stochastic signal. This one is the pure signal, sine signal. So it's going to be looking like something like this. Okay, call it. So if you look at this signal, you already see the frequency, but quite often you don't see that. You don't see that directly seen. But if you're having now in the energy spectrum, or you have the autocorrelation, just by looking at this peak here over there, you can say, ooh, there's a dominant frequency. There must be something happening. That's something I can either control, I can enhance it, or I can try to attenuate it, so depending on your application. So, and with that, you can now use the energy spectrum and the autocorrelation to analyze the signal, and that tells you a bit more about what is going on in the flow.